Hello, everyone. Hope you're having an awesome day. Thanks for joining the SN Applied Sciences webinar series. I see some of the attendees are from India. We have from Indonesia, I guess. China, I see the Netherlands, also the US. Thanks everyone for joining. I think you all know the drill before we start. Please mute yourself, except from the co-host, of course. Please mute yourself, and if you're not already muted, and turn off your camera as well. If you had any questions during the webinar, please type it in the chat box. We have an official Q&A at the end as well that you can propose your questions. Today, we are delighted to be joined by Professor Mescher from University of Washington for the second time, actually. We enjoyed the first webinar so much and requested Professor Mescher to join us for a second time, and she kindly accepted. I give a brief introduction to her, and then I will pass it on to her to present her interesting piece of work. So Anne is a recognized researcher with over 25 years of experience that spans over a variety of subjects, such as energy transfer, thermal fluid sciences, manufacturing, and materials processing, as well as solar and geothermal energy transfer. She enjoys teaching graduate level radiation, conduction, and convection heat transfer courses, thermodynamic and fluid mechanics. In addition, she maintains a strong interest in capstone design projects, having led and organized several of the University of Washington Mechanical Engineering design fairs with support from an industrial advisory board. I think we are all set to start the presentation. Anne, thank you again for joining, and please go ahead with your presentation. Thank you.
Good afternoon, everyone, and thank you so much for joining from wherever you are. It's just wonderful to have this opportunity through Springer Nature's webinars to present this work. I'm just delighted my co-author is here, Laurel Tauser. She is a master's student at the University of Washington Department of Mechanical Engineering. And this is our work on the alignment of microcrystals in drawn fiber. And our goal is to achieve alignment for these small scale structures over macro scale lengths, whether that's from submeters, even up to kilometer length scales. So this particular project has as its goal to align microstructures in the first stage, and then ultimately our goal is to align nanostructures as well. And this is to extend what are sometimes exceptional properties in these very small scale structures, thermal properties, optical, electrical, and or mechanical properties. And again, the goal is to harness that the properties that are desired, those exceptional properties, and extend them to the macro scale. So before I talk about what Laurel and I did together, I'll review what is reported in the literature with regard to aligning these small scale structures. So the simplest method is one where you have the small scale structures positioned on a substrate that is deformable. And you can think about just a rubber band in the simple case, and the small scale structures are placed such that they are not going to come off of the deformable medium, and then the substrate is deformed, stretched. And it's clear that as you stretch the material, There is a positive correlation between the strain, the amount of stretching, and the degree of alignment achieved. Another common method that you would see in the literature are extrusion methods. And extrusion methods have been used with a variety of small-scale structures, including carbon nanofibers, as shown in this publication from 2005. And with polymers as the host material, incorporating the small-scale structures, you typically just single screw extruder, and the composite material is forced through a die. With metal composites, it's the same basic operation. It's forced through die and pulling on the exit as the composite material is coming through. And these sorts of processes can be repeated. So there are multiple extrusions, regardless of the host material into which the small scale structures are incorporated. There are these mechanical forces that are tending to cause alignment. The small scale structures need to have sufficient aspect ratio, but here you're seeing the carbon nano-sized fiber as it's going through the die, the restriction and some degree of alignment is achieved. The more draws you do, typically the better the alignment will be. Okay, and now in the next slide is a direct spinning process that's illustrated here in the A, B, C, and D, but there are a number of different methods of spinning fiber. So the particular one that's shown here is a dry spinning process from a forest of carbon nanotubes. So you can see in the images, here are the nanotubes. They're being spun into an individual twisted fiber D. And this is a way to get a fairly high strength yarn from carbon nanotubes that are coming from this forest of nanotubes that have been grown. Another process fairly closely related is producing a carbon nanotube aerogel using chemical vapor deposition reactor, and then twisting the fiber from that carbon nanotube aerogel. Wet spinning processes basically are aqueous solutions of carbon nanotubes injected into a polymer coagulant. So a number of variations, but all of these are basically assembling through spinning processes. Then there's dip coating. Dip coating involves a liquid, and the small scale structures get some sort of a hydrophobic coating so that they are suspended on the liquid surface. And then you take a substrate and you pull it upwards, and the forces in the liquid near the meniscus are going to generally tend to produce some degree of alignment if, again, the aspect ratio is sufficient, so that the alignment is in the direction of the pulling direction. So here you're seeing an image where you have silver nanowires, and there's some heat assistance here to drive off moisture so that the fluid dynamics in the meniscus region is aiding the movement of liquids such that the nanowires are adhering to the substrate glass in this particular case. There are a variety of methods that you will find in the literature. And here this is a small list of some of the other methods that are cited. One of the oldest is the Langmuir-Blodgett, but that's been revitalized recently, and it is fairly widely used. So the image on the right shows a barrier, and it's then moved to concentrate the nanostructures. And then again, in this process, a substrate is moved upward, picking up the small scale structures and producing a film. Magnetic fields have been used, and if you have small scale structures that have magnetic properties, then you can use magnetic field, electrical field, strain release processes have been used and cited in the literature. Processes that involve evaporation to produce capillary forces and an alignment based on those capillary forces, contact and roll printing, as well as blown bubble films. So this list is not exhaustive, but it's at least a start on the various methods that have been used for aligning small scale structures. All right, so now our method, and that was recently developed, and I'm very, very pleased about this. The Polymer Optics and Processing Lab at the University of Washington has been in operation now for 2.5 decades, and this has definitely been a highlight with regard to fabricating fiber, in this case with alignment of microcrystals. So here we begin with the preform assembly. I'm going to talk first about the assembly of this larger scale rod system, in this case a tube and a rod together, that is then drawn into fiber. Now, to contrast this against the die extrusion process that I showed before, this material will never be forced through a restriction, a die. The drawing process is distinctly different, but the preform is heated and then it's pulled on in order to produce a much smaller diameter fiber. So I'll show you the drawing process in the next slide. But to begin with, we want to look at the assembly of the preform from which the fiber is drawn. So we begin with a rod, in this case, just standard acrylic. Its outer diameter is 9.3 millimeters, and a surrounding acrylic tube. And the key dimension is its inside diameter of 9.65 millimeters. So there's an interstitial gap, and that gap, if the rod and the tube are concentric, is 180 microns. Now, this is a cross section of what looks like, this is the preform from which fiber was drawn with the aligned microcrystals. So this is the cross section, and this interstitial gap is what holds the suspended microcrystals. The asymmetric case, or the acentric case, is the one where the rod and the tube wall are in contact on one side, and then you have a larger gap. So I just want to point out an extreme case where the gap could be as large as 360 microns. There's my cursor. So The assembly process involves suspending the microcrystals in oil. In this case, it was grapeseed oil. And then putting this section of preform into a longer rod, which can then be drawn into fibers. So it turns out that the ends of the preform are sacrificial. We could have made this intersection with the oil and the microcrystals incorporated longer, but this is just a short test section. And in any case, there will always be sacrificial ends because of the batch nature of the fiber drawing process. So what's important to note that with the microcrystal dimensions, which I'll show in the next slide, it turns out that this dimension, these dimensions of 180 microns and 360 microns, are large relative to all the dimensions of the microcrystals. That means that they are free to orient in any way as they are suspended in this oil. So they do not possess any significant alignment in the preform that's going to be drawn into fiber. All right, so now here is the drawing process. And this will take some time to explain, and I'll be happy to come back and revisit it if you have questions at the end. But in summary, you have a preform that is fed at a constant slow speed into a cylindrical heater. And as the material heats up, the material goes through glass transition. Now, the oil was chosen such that it would not become volatile at the temperatures that we're drawing at. And for most of the polymers that we are processing, the maximum temperatures in the system are less than 200 degrees Celsius. But whatever composite material system you choose, you want to make sure that you're not driving off volatile components that you would want to keep there. You would want to make sure that you're not causing any deformation of smaller scale structures that you would like to retain the shape of. So the beauty of polymer processing is it happens at much, much lower temperatures than would be processing glass. And thus you can incorporate a much wider variety of materials than you could in a glass fiber process. In the case of polymer fiber production, the primary modes of energy transfer in this cylindrical heater are convection and radiation. And you'll notice here what we call a top iris. There's actually a seal here so that air doesn't move up and out of the system. Now below here is labeled the bottom iris. This is not a die. The material is not being forced through a restriction. So there's free space between the fiber and the wall of the bottom iris. But because of this seal at the top, O-ring seal, there is not upward gas movement. So in this case, it's natural convection of air and radiation transfer that raise the temperature of the polymer above glass transition. You really don't want it that far above glass transition, just a bit. And then the material will neck into the fiber diameter. And as long as you're providing a fairly uniform tension, and as long as the convective patterns inside of the cylindrical heater are stable, you'll get a fairly consistent diameter. So the preform diameter, we're calling that capital D, the fiber diameter, small d, and the fiber velocity, V sub f, is what's used in the drawing process to control that fiber diameter, the outer diameter. That makes it possible to control as well the width of that interstitial gap between the inside rod and the outer tube of the preform that I showed in the previous slide. So that preform, that larger diameter cross section that I showed you before, basically gets elongated, stretched. And the length of the fiber that you end up with, of course, is orders of magnitude greater than the length of the preform that you started with. You can draw kilometers of fiber from a 1 meter length preform. But the key is that, and this is in contrast to the die extrusion process that we showed earlier, the key is that every geometric dimension in the cross section is maintained similarly, geometric similarity in the final fiber. So if the ratio of the rod diameter to the outer diameter is half, then that's what it's going to be in the fiber. And so you can scale down as you scale the preform diameter capital D down to the fiber diameter small d. You can scale every dimension in this preform, scale it down by the same factor in the final fiber. So here you're just seeing the process as the fiber is taken up on the fiber spool. All right, here's a little bit about the microcrystal morphology. We were looking for microcrystals that had an aspect ratio of about 10. That's 10 times longer than the width or the diameter. And we were looking for stiff microcrystals. So these are ytterbium doped potassium lutetium fluoride microcrystals. And you can see the distribution for a fairly small number of crystals on their length, ranging from 20 to 120 microns. And then their width or diameter ranging from 2 up to 18 microns. So the bulk of the microcrystal diameters appear to be between 6 and 10 microns. And the average length of these microcrystals is around 67 microns. The aspect ratio turns out to be right around 8, but that was sufficient for our process that we're using to illustrate the alignment of these microcrystals. So again, keep in mind that average diameter of about 8.4 microns and that length over 50 microns. So notice here the 50 micron scale for these crystals. A lot of these crystals are separated individual, but there are some that grew together. They're hard linked, and that resulted in some misalignment. But you'll see with the individual crystals, we were able to achieve excellent alignment. All right, let's talk about the mechanism, and then I'll show you some results. So we remember that the cross-sectional geometry that I showed you in the slide with the preform, that cross-sectional geometry is maintained during the draw process with complete geometric similarity. In these experiments with the KLF microcrystals that I showed you, the draw ratio was about 20. So the preform diameter divided by the fiber diameter was roughly 20. In most draw processes, it's easy to achieve draw ratios of 100 or less. And you can even draw more than once, just like with the extrusion process. Multiple extrusions produce better alignment. In this drawing process, you can cascade fiber, bundle it, and then redraw that fiber bundle to produce drawdown ratios of over 10,000 just in 2 draws. So you can readily get a drawdown ratio on the order of 100 in a single draw, and then 100 times 100 in a dual stage draw. But all the results that you're seeing today are just with that simple drawdown ratio of about 20. So here we note that this liquid-filled gap that started out at 180 microns in the concentric case is also reduced by a factor of 20. And in the preform, if you recall the dimensions of the microcrystal, on average, they're 67 microns long. On average, they're 8.5 microns in diameter. And so because this gap is in the concentric case 180 microns wide, and in the worst acentric case, it's 360 microns wide. Again, those crystals are free to orient just about any way they want. But as the preform diameter here is drawn down to the fiber diameter, where that ratio of preform diameter to fiber diameter is 20, that gap is also reduced. So what was a 180 micron gap becomes a 9 micron gap in the concentric fiber, where the rod is right in the center of that tube on the same axis. And in the worst case, where it's acentric, the widest gap is 18 microns. So what you can see here is that as that gap becomes much narrower, the microcrystals are no longer free to orient in any direction. They have to align along the draw direction, along the fiber axis, parallel to the fiber axis. So this image here on the far right is attempting to illustrate that point, that the microcrystals can orient randomly in the gap. But by the time you get down to the necking region and the fiber, they are constrained to align parallel to the fiber axis. So the key in terms of the processing and how we control this fiber outer diameter, and thus the gap in where the microcrystals are suspended in liquid, notice that this concentric case, the 9 micron gap width, is on the same order, very close to the average diameter of the microcrystals. And that turns out to be pretty important. If it were much bigger, you wouldn't have as much alignment as we have seen in these results. And if it were smaller, there would be other issues with deformation of the inner rod material of the polymer and the outer tube. So another key difference between this drawing process and the extrusion process that I showed previously is that this polymer material doesn't really go through a melt. It's a glass transition. And so the material becomes soft and it can be pulled and permanently stretched, but it's not as though this polymer can flow like a liquid. The oil is clearly in the liquid phase. It allows the microcrystals to be free to orient themselves as they are geometrically constrained to do. but the polymer material itself is relatively firm because we are not raising the temperature of the polymer well above its glass transition. So it's firm, and it's providing the geometric constraint for those nanocrystals to push up against, so that they, again, are constrained. It's like a funnel, kind of. You can think about spaghetti noodles before you cook them in two concentric tubes, right? And if the diameter of those two tubes is chosen, diameters of those two tubes are chosen correctly, the spaghetti can only orient one way because of the curvature of the tubes. It's also interesting to think about in the draw process. For example, you could take two acrylic sheets or two polymer sheets, and you could put a film of nano or micro structures between those two sheets, and you could draw those sheets into that preform into a ribbon assembly. But if you think about it, while you would have a layer of small scale structures between the two polymer surfaces, there's not sufficient constraint, right? They would be constrained to be in that plane, but there is no curvature to force the constraint in the perpendicular direction. So with the curvature, you are constraining such that the axes of the small scale structures have to align perpendicular or parallel to the fiber axis. They have no choice because of the curvature. And you're reducing, if you think about the radius of curvature as you go from the preform to the fiber, you're reducing that radius again by a factor of 20, and that constrains the orientation. So of course, the small scale structures are free to be in any azimuthal position, but typically you'll have the small scale structures at various positions with regard to the azimuthal coordinate. And so what that tends to do is it gives you a fiber that tends to be concentric. Why? Because the average diameter of these particular microcrystals is on the same scale, about the same as the gap in the concentric case. So again, with proper choice of the drawing conditions to create a specific gap width, you can end up with fairly good concentricity because you have them at various azimuthal positions. So you can't really skew the rod inside of the tube. Now on the preform, you can have significant significant eccentricity, but by the time you get down to the fiber, because you're matching the diameter of the small scale structure and the gap width, by that point, it's got to end up being fairly concentric on average. Okay, so here's just an image from an optical microscope showing individual crystals aligned along the fiber axis. I'll point out with my cursor, here's a microcrystal, here's another one. Here's one, here's one, here's one, and some others over here, but I can't quite see those because I'm looking at the participants. And it turns out those were quite well aligned. But notice here, a little bit out of focus is a V-shaped crystal, and that's a hard linkage. That is not well aligned, and it's because of its geometry. Such a crystal would also result in some eccentricity. And here we need to look at this effect a little bit further, deeper, but in a process where you have a hard linked crystal like this, not an individual rod, it is likely that in that drawing process, as you are reducing down to the smaller outer diameter, the ends of the rods that are hard linked are going to be rubbing up against the polymer surface. And so you would expect some damage around the inner rod and the outer tube of the acrylic, wherever you have hard linked crystals that are not going to be able to align with their axes parallel to the fiber axis. We saw a fairly nice correlation. There's obviously some scatter here, but as we analyzed the individual crystals, we saw that they were aligning within 3 degrees of the fiber axis, the draw axis. And we also see the scale is from 3 degrees to 1. And we also see that as the microcrystal becomes longer, the deviation angle becomes less. And that's what you would expect. With shorter crystals and that radius of curvature, there's a little bit more freedom to be oriented increasingly off axis. So the key is sufficiently long crystals. Again, you're shooting for aspect ratios on the order of 10 or perhaps higher. They need to be stiff and with diameters on the order very comparable to the gap width in the fiber. We used image J, that's open source, to measure the angle of deviation from the fiber axis. All right, so that's it. A very short presentation compared to the first presentation I gave, which went way over. But in conclusion, we're presenting a method here that, as far as I can tell, has not ever before been reported in the literature as a method to align small-scale structures. Again, the structures need to be stiff in this sort of process. You'd have to have an aspect ratio on the order of 10. And in this particular process, we've been able to demonstrate that for individual crystals, you can align them to within a few degrees of the fiber axis. So we'd like to further develop this method where we ensure that the small scale structures that we're using are fairly purely individual crystals, so that we don't see the misalignment that we saw with the V-shaped crystal. But really what we're aiming for long term is multi-stage drawing processes, because we'd like to cascade tubes within tubes, and we'd like to have dual stage or even triple stage draws, so that we can get that interstitial gap down to the nanoscale. And if we can do that with the right sort of nanostructures, then it will be possible, we think, to align nanostructures as well as microstructures. And again, the exciting thing about this is that when you start out with a preform that's on the order of 0.5 meter or 1 meter, you end up getting fiber that's kilometers in length. So what makes me really, really happy about this is that we're talking about very small scale structures, but being able to align them over really macro scale lengths. So we're hoping for some collaborators. We're mostly interested in optical applications, but we're wondering if there are any biomedical engineers that might have some biomedical applications in mind. But just really excited because at least I have not seen in the literature methods that allow you to align such small scale structures over really big macro lengths. So just to acknowledge, we have a few acknowledgements here. Our work was supported by the National Science Foundation, and in particular, I'm a huge fan of REUs, the research experiences for undergraduates, and that's how Laurel started. I'm not sure she'd be in a graduate program if it were not for the REU experience, and that's how this project started. We are very pleased to acknowledge Professor Peter Pazowski and his graduate student Zhaojing Jia. She synthesized those microcrystals and looked at the characterization for us, basically filling the bill when we said we need aspect ratio of 10 and such diameter and stiff. She said, okay, I've got just the thing for you. So we're very pleased about that collaboration. So hope you've got some questions for me, because we have a lot of time. We have we have a whole hour allocated, as I understand.
Yes, indeed. Professor Mescher, thank you very much for the interesting presentation. It was quite an interesting, complete, experimental work. I enjoyed listening to it. We have a number of questions actually in the chat box. I don't know if you can read the chat box directly yourself, but I'm just going to read the questions one by one out loud. We have from r.ambarasan that asks, I think from one of the initial slides, 0D, 1D, 2D, 3D, which is giving better fiber performance as you presented in the slides?
Okay, I'm going to try to go back to the slide. Okay, so this is a question on the on our method or on another method?
Well, let's do both. Your method compared to the other methods, let's go that route.
Okay, so for our method, the structures should be rod-like. They should be rod-like and with aspect ratio at least 5 to 20 is best. So these are really one-dimensional structures. They can be paraplelepiped, they can be rectangular, or they can be rod-like. Any geometry is fine, provided that the width dimension is on the order of a tenth of the length dimension. Now, in other processes, as far as I understand, so much of this alignment work was really started when carbon nanotubes were first reported. So 1980-ish was when there was just a lot of effort. And so when you look in the literature, so much is really, I mean, here I'm showing in one of these slides, it's silver nanowires, but in all of these processes, you'll notice that, for example, what's the limitation here? The limitation is, okay, you're putting on this substrate these small scale structures and they've got an aspect ratio, but your limitation is how far you can stretch it and that you have to have a flexible substrate. And sure, you might be able to transfer them, but in the transfer process, you may have some misalignment as well. So this 1D stretching, for example, there's limited success with it. Why? Because you clearly have constraint. It's the material's on a planar surface and you're stretching it such that you're going to get some degree of alignment, but there is nowhere close to alignment within a few degrees in this sort of method. Same thing with the extrusion processes. You can do multiple extrusions, but if you think about it, really, in this process, the polymer host or the metal host is not in any significant way constraining. There's no constraint. There are forces that are acting, on the small scale structures that will tend to align them. But and for example, as we cite in the paper, with carbon nanotubes embedded in copper composites, you get multiple, improvements. You get a factor of 2 or more increase in the strength of the composite compared to the material without the reinforcing carbon nanotubes. But your degree of alignment is always measured relative to a perfect alignment. You can't get it because the forces in the matrix are really, they're just forces. They're not hard geometric constraints. Carbon nanotube, that's its own class. You're just spinning the carbon nanotubes themselves into a strand. And this dip coating method, there are hybrid methods, for example, with the Langmuir-Blodgett and dip coating, where you can treat the surfaces in such a way that you get pretty good alignment. But I would say that the limitation is you're not going to get kilometer length scales, not with a Langmuir-Blodgett. In a fiber, the material is now incorporated in a fiber. And so, it's not trivial to get it aligned back out of the fiber. You have to have a compatible, for whatever your application is, you have to have a compatible host with the nanostructures that you want to take advantage of. So I'm not sure I answered the question, because the question sounded like it was really, what's the advantage of a one-dimensional, two-dimensional, three-dimensional structure? But I'm thinking about, in our case, and in any of these cases, it could be a parapolipid, it could be a cylindrical rod, as long as the length is on the order of 10 to 20 times higher than the width dimension. That's the key.
Okay, thank you very much for the detailed response. Let's go to the next question from Indonesia, Ahmad Salihin. And he asked Professor An, should the microcrystals be in hydrophilic nature, hydrophobic nature, as suspended in oil during polymer fibers drying?
Yeah, so you want to make sure, of course, that the fluid that you choose, there's a number of constraints on the fluid that you choose for that interstitial gap. You've got to have good wetting. So in our case, it's an oil. And we also wanted to make sure in our case that we could contrast the refractive index of the KLF microcrystals relative to the refractive index of the oil. We had to be sure we could actually see them when we just put them under an optical microscope. So those are the sorts of compatibility questions you have to ask. And in that drawing process, we could have chosen some oils that would have started to have some lighter volatile components being driven off. The maximum temperatures in that particular drawing process were probably right around 160 to 170 degrees Celsius. So you got to be sure that you're choosing something that's not going to start to volatilize. But in all these other processes where there's no heat involved, you have a lot more flexibility in terms of the fluid that you're using, provided that, once if the fluid is going to evaporate, you want to make sure that the structures are staying where you want them to be.
Okay. He continues, have you tried using lingocellulose materials such as cellulose for polymer fibs drawing? And if yes, have you added some polymers such as PLA or PVA? And what conditions can cause the polymer deformation as the final gap size range is below microcrystal average diameter? Do you have any treatments to achieve the gap size range similar to microcrystal diameter?
Well, in the results that we showed, the gap distance is very close. It's just slightly larger than the average crystal diameter. So you can control that in this drawing process by controlling the outer diameter. Remember, the ratio of the gap width in the preform to the outer diameter is going to be preserved. So all you do is you control the outer diameter. And the way you do that is by controlling the draw speed. So it's under steady state operation, it's a mass conserving process, right? The cross-sectional area times the incoming velocity is equal to the cross-sectional area times the outgoing fiber velocity under steady state conditions, because you have practically no change in density. So you can easily control the outer diameter and therefore the gap dimension. I would say the most important thing is with the material that you're incorporating, you want it to be fairly mono. You don't want a wide distribution. I showed you that we had a fair number of counts with regard to the length. I think it was a minimum of around 20 up to 120 microns in length. But with this sort of process, you really want some pretty good constraints on the diameter. If you have a wide range, then you're going to have less and less concentricity, right? Because different diameter rods are going to cause movement of that rod inside the fiber relative to the tube. So you want something pretty mono dispersed with regard to the diameter. And in our case too, it has to be stiff. So with regard to cellulose, unless you were able to treat the cellulose fibers in such a way as to make them stiff, this particular method would have mixed success. If you don't care so much about twisting, okay. But if you really want them aligned, it does need to be a stiff material. You'd have to process them in such a way as to make the cellulose fibers stiff.
Okay, thank you very much. Well, we have no more questions in the chat box as of now, but the audience, you should know that you can reach Professor Ann Mescher through email if you had further questions. You can also refer to this video recording at a later time to watch it again and gain more insight. And but for the time being, I would really like to thank you, Professor Mescher, for giving us the time and attend the SNES webinar series. And if you have something else to say, other than that, we can close the session.
Very good. I appreciate everyone's attendance, and feel free to reach out if you have any interest in applications that would take advantage of this sort of alignment, or if you have materials that you would like to see incorporated into a fiber structure, we would be happy to incorporate your materials. We had no role in the synthesis of these structures. We just said this is the sort of structure that we want. And so if you have a particular structure that you would like to see aligned, we would be very receptive to that opportunity. Okay, thank you very much. Thanks everyone for attending the webinar. And some people are just sending their salutes to you and also writing in the comment section. So thank you again, and hope to see you in another webinar series, hopefully early next year. Thank you, everyone. Have a good day and goodbye.